Ancient Greek atomism. Did Democritus predict quantum physics? Ancient Greek philosopher Democritus, 460 to 370 BCE, is considered one of the pioneers of atomic theory. The idea that the universe is composed of small, indivisible, and unchangeable particles, atoms, was a radical concept in his time. The notion that atoms had different shapes and sizes and moved through a void challenged classical natural philosophy. Although Democritus' ideas are not directly related to modern advanced physics theories, they laid the foundation for atomic thought, contributing significantly to the history of science. Some scholars suggest that, in a sense, Democritus may have predicted quantum mechanics. In this article, we will examine the fundamental principles of ancient Greek atomism, its similarities and differences with modern quantum mechanics, and Democritus' place in the history of science. Democritus and the foundations of atomism. Democritus' teacher, Leucippus, is regarded as the founder of atomism. However, it was Democritus who systematically developed and refined the theory. According to atomism, all matter is composed of an infinite number of indivisible and unchangeable atoms. Atoms have different shapes, sizes, and weights. These atoms move randomly through a void and combine to form various objects. Material changes occur when atoms join or separate. The universe operates entirely through mechanical processes, without the need for supernatural intervention. This idea directly opposed the views of Plato and Aristotle. Plato saw matter as a reflection of ideal forms, while Aristotle supported the continuity of matter and the four-element theory. Democritus' mechanistic and particulate vision of the universe is much closer to contemporary scientific thought. Similarities between Democritus' atomism and quantum mechanics. Although Democritus' atomism presents a much simpler model compared to modern physics, it shares several fundamental concepts with quantum mechanics. 1. Indivisibility of atoms and quantum particles. Democritus described atoms as indivisible and infinitely small. Modern physics has discovered that atoms are composed of protons, neutrons, and electrons, but quantum mechanics still recognizes some fundamental particles as indivisible. For example, quarks and electrons are among the smallest known fundamental particles. 2. Random motion and probability. Democritus' atoms moved randomly through a void and formed different objects through collisions. In quantum mechanics, particles do not follow specific trajectories but exist within probability distributions, defined by wave functions. 3. Concept of the void and vacuum. Democritus proposed the idea of a void in which atoms move freely. Although this idea was rejected by Aristotle and many other ancient philosophers, modern physics has demonstrated that space is largely a vacuum, where particles move freely. 4. Wave-particle duality and atomic motion. Although Democritus did not explicitly propose wave-particle duality, his notion of randomly moving atoms bears a resemblance to the way modern quantum mechanics describes particles as exhibiting both wave-like and particle-like behavior. Key differences between ancient atomism and quantum physics. 1. Lack of a mathematical framework. Democritus' theory was entirely based on philosophical reasoning and lacked the mathematical precision of modern quantum physics. Quantum mechanics is built upon rigorous mathematical frameworks such as Schrödinger's equation and Heisenberg's uncertainty principle. 2. Absence of energy quantization. A fundamental principle of quantum physics is that energy is quantized and exists at discrete levels. This concept is absent in Democritus' atomic theory. The idea of energy quantization, proposed by Max Planck in 1900, far surpasses Democritus' speculation. 3. Internal structure of atoms and particle physics. Democritus envisioned atoms as solid, unchangeable particles. In contrast, modern physics has revealed that atoms consist of protons, neutrons, and electrons and are far more complex than Democritus imagined. 4. Observer effect and uncertainty principle. In quantum physics, measuring a particle's state affects its wave function, as described by Heisenberg's uncertainty principle. Democritus' theory did not account for the observer's influence on matter. Impact of atomism on modern science. Although Democritus' atomic theory did not directly predict quantum physics, his ideas paved the way for the development of modern science. In the 17th century, Pierre Gassendi revived Democritus' ideas, and in the 19th century, John Dalton's atomic theory built upon them. Eventually, these concepts merged with the discoveries of early 20th century quantum physics, laying the foundation for modern subatomic particle physics. Democritus' atomism shares many conceptual similarities with modern quantum physics, yet it remains more of a philosophical speculation rather than a scientific prediction. Nonetheless, his attempt to explain matter in terms of indivisible particles has secured him a significant place in the history of science. Although ancient Greek atomism is not regarded as a direct precursor to modern physics, it contributed to humanity's ongoing effort to understand matter. The idea that the universe is composed of the smallest, indivisible units continues to provoke deep philosophical and scientific thought even today.